Okay, in this lecture, we will define the dual space and discuss some of its properties. So we start by a definition of what we mean by linear functional. So let's start by a definition. So let V be a finite dimensional vector space let V be a finite dimensional vector space over a field F. Over a field F. A linear transformation F from V into the field F is called a linear functional on F. Is called a linear functional on V. Is called a linear functional on V. So thus linear functionals are special kinds of linear transformations. A linear transformation is usually defined to be a linear map between two vector spaces. Now here, this linear functional is a special kind of a linear transformation. It's a linear transformation or a linear map from a vector space V over F to the vector space F over F. And since we know that every field forms a vector space over itself, so therefore this kind of a linear transformation. So therefore F of F is a vector space over F, and V is also a vector space over F here. And any linear transformation from V into F is specially named as a linear functional on V. Now, before going into the definition of how we define a dual space, we shall take certain examples of these linear functionals. For example, a linear transformation F from Rn into R defined by f of x1 through xn. This is equal to a1 x1 plus so on plus an xn is a linear functional, or we can skip the term linear and just call it a functional. Is a linear functional on Rn. It can easily be verified that this is a linear transformation. But now since it's a linear transformation from Rn into R, and we know that Rn is a vector space over R, and R is also a vector space over R, so therefore a linear transformation from Rn into R defined in this way is a linear transformation, and this kind of a linear transformation is specially known as a linear functional on R. So it is easy to check that. It is easy to check that F is linear. Now, before giving more examples of the linear transformations, we will prove that if we have any linear functional from Rn into R, then it has this kind of a shape. So let's do it in the form of a proposed or a remark. Any linear functional on Rn is of the form is of the form a1x1 plus a2x2 plus so on plus an xn for some real numbers for some a1 through an in R. So if we have these real numbers a1, a2, an in R, then any linear function on Rn has this kind of a form. So in fact, we can prove it. So suppose if possible, suppose G is any linear functional. Suppose G is any linear functional on Rn. Now we know what is the standard base of Rn. Let this E1, E2, so on, En be the standard basis of Rn. Be the standard basis of Rn. So then f of ei, sorry, no, it is actually g of ei, since we are taking this g to be a linear functional on Rn. So then let g of ei is equal to alpha I. Now, how we can write it, because we have this g is a linear functional on Rn. So that means g is a linear transformation from Rn into R. So therefore, now since these are the base vectors of Rn, so therefore every base vector when evaluated under this linear functional on Rng, when any base vector is evaluated under this linear functional g on Rn, then g of ei will be some real number in R. So let's call that real number which is associated to ei under the linear functional g to be alpha I. So where alpha I is some real number. Now since this e1, e2, en is a basis of Rn, so if we choose any vector x in Rn, then that x can be written as a linear combination of these basis vectors. So now let x is equal to x1, x2, so on, xn belong to Rn. Then we can write, then we can write, x is equal to e1 x1, or better to write x1 e1. So then we can write x1 e1 plus x2 e2 plus so on plus xn en. Since these ei's are the base vectors, so therefore the ith coordinate of ei is equal to 1 and all the remaining coordinates of ei is equal to 0. So therefore if we have this linear combination x1 e1 plus x2 e2 plus xn en, then this linear combination is an n tuple whose ith coordinate is xi. And since x has its ith coordinate equal to xi, because we have taken this x equal to x1, x2, xn, then this can easily be seen that x equal to this thing is the same x. So now, so then we will evaluate this x under the linear transformation. So we will now evaluate this x under the linear functional g. So then g of x. Now this g of x is equal to g of this x1 e1, sorry, x1 e1, x2 e2, plus so on, plus xn en. Now since g is assumed to be a linear functional, so it's a linear map, so therefore we can write this is equal to x1 g of e1 plus x2 g of e2 plus so on plus xn g of en. Now, by definition, we have, since this G is a linear transformation, it's a linear functional from on Rn, and we have defined this G of ei is equal to alpha I. So using this thing now, so therefore G of e1 can be put equal to alpha 1. So this first coordinate is, first term is x1 alpha 1 plus second term is x2 alpha 2 and so on. And this one is xn alpha n. So thus, this g of, now this x, it is equal to x1, x2, xn. So now this is equal to alpha 1, x1 plus alpha 2, x2 plus so on plus alpha n, xn. So we have actually proved that every linear functional on Rn is of this form. So thus, every linear functional on Rn is of the form a1 x1 plus a2 x2 plus so on plus an xn for some real numbers. Sorry, not actually the, yes, actually the real numbers point source for some real numbers a1 to an. So this was our first example of a linear functional. Now let's take few more examples. So let's have example number 2. Now a linear transformation, a map f from the set of all n cross n matrices over the set of real numbers into R. Now this is mn cross n denotes the set of all n cross n real matrices defined by f of A is equal to trace of A. So then this is a linear functional. So here every matrix is mapped to its trace. Now since the trace is defined to be the sum of the diagonal entries of a matrix, and here we are choosing this to be the set of all n cross n matrices. So trace of A will be the set of all diagonal entries, and since all the entries in every matrix of mn across n are real numbers, so therefore trace of A will be the sum of n real numbers in an n cross n matrix. So this is a real number. So therefore f of A equal trace of A also defines a linear function. And we can easily see that this is also a linear transformation. So since this trace function is a linear function, since trace of alpha A plus B, this equal to alpha times trace of A plus trace of B. So thus the linear transformation f from mnr into R defined by f of A is equal to trace of A is a linear functional on the set of all n cross n real matrices. Now let's take one more example. Let V be the vector space of all continuous functions on some closed interval AB. Now this V over R is a vector space. Then V over R is a vector space. Now if we define a mapping, define a map F from V into R by f of some continuous function. Let us denote this continuous function by some notation. Let us denote by p of x. This is equal to integral of p of x from a into b. So if p of x is any continuous function in the set of all continuous functions on the interval a, b, then a map defined by f defined from v into r by f of p of x is equal to integral from a to b p of x dx. Then since this integral is also a linear transformation, this integral is also a linear function. So this is a linear transformation, and now since the integral from a to b, this is a definite integral, it's a real number in ab. So it is a real number in r. So this function from v into r is also a linear functional on the set of all continuous functions. So then f is a linear functional. So these were certain examples of the linear functionals. Now we can proceed further and discuss some properties of the linear transformations, linear functionals and the dual spaces. Now, before define the dual space, we shall recall something. We shall recall the set of all linear transformations between two vector spaces. Recall LVW that we had defined in the previous lectures. This is the set of all linear transformations. This is the set of all linear transformations from a vector space V into a vector space W. Then we had also seen that this L of VW is a vector space. We are seeing that this is a vector space, and the operation is defined by under the operations the internal composition was defined in this way: T of T1 plus T2 of V. This was defined to be equal to T1 of V plus T2 of V. So this was the internal composition on V on this LVW, and then the external composition was defined in this way: T of alpha times V. This was defined to be equal to alpha times T of V. Then under these two, this is the internal composition and this is the external composition on LVW. Then under these binary operations, this LVW forms a vector space. Moreover, we had seen that if dimension of V is finite and dimension of W is finite, then this dimension of the vector space, the set of all linear transformations from V into W, this was defined to be equal to dimension of V into dimension of W. So these were certain properties of the set of all linear transformations from V into W. It forms a vector space under these binary operations, and if both have the finite dimension of V is finite and dimension of W is finite, then the dimension of the vector space of all linear transformations from V into W is also a finite dimensional vector space, and its dimension is equal to dimension of V into dimension of W. So now let's come back to our linear functionals. So we can define now, since we have a mapping, a linear transformation from a vector space V into the underlying field, which is also a vector space, then this kind of a linear transformation is now known as a linear functional. So as we have discussed the set of all linear transformations between two vector spaces, so now let's have a look at how the set of all linear transformations between these two vector spaces look like. So now a definition. The set of all linear functionals. The set of all linear functionals between V and F is denoted by V star and is known as the dual of V. So what is dual of V? Dual of V is the vector space of all the linear functionals from the vector space V into the underlying field F. So now here this field is also a vector space. So the set of all linear transformations between these two vector spaces, where V is assumed to be a vector space over F and F is assumed to be a vector space over itself. Then the set of all linear transformations from V into F is already known to be a vector space. But now this vector space is usually denoted by V star and is known to be the dual of V. So now let's have a result that relates the basis of V with the basis of V star. So before doing the result, we shall have some observations which quickly follow from the set of all linear transformations between V into W being a vector space. So let's recall it in a form of a proposition. This L, sorry, not L, but this V star. V star is a vector space. V star is a vector space. Also, if dimension of V is equal to n, then dimension of V star, this is also equal to n. And this straightforward follows from this fact that if we have two finite dimensional vector spaces, then the set of all linear transformations LVW has a finite dimension that is equal to dimension of V into dimension of W. But now since this dimension of V is equal to n, and F is a vector space over F which has dimension equal to 1. So therefore dimension of V star, that is equal to dimension of V into dimension of F over F. So this n into 1, and so this is equal to n. So therefore the dual space is also a vector space of dimension n if V is a vector space of dimension n. Now let's have one result. This is in the form of a theorem. Now let V be a finite dimensional vector space. Let V be a finite dimensional vector space with ordered basis V1, V2, Vn over a field F. Then there exist linear functionals. Then there exist linear functionals F1, F2, Fn, such that for each I, this f of I of Vi is equal to 1 and Fi of Vg is equal to 0 whenever I is not equal to G. Then the set of these linear functionals F1, F2, Fn. Then F1, F2, Fn forms a basis of V star. So therefore, what this theorem states is that if we have a finite dimensional vector space with ordered basis V1, V2, Vn, then from this ordered basis, we can construct the ordered basis for the dual. And the ordered basis is denoted by F1, F2, Fn, while Fi is defined to have its image under the ith coordinate vector, ith vector equal to 1. So Fi of Vi is equal to 1 and Fi of Vj is equal to 0 whenever I is not equal to j. So this theorem actually gives us a relation between the ordered basis of a vector space V and the ordered basis of its dual. So this also actually helps us in the construction of the ordered basis for the dual once we are given the basis of V. So we will prove the theorem and then we will take some examples of how we construct the ordered basis for the dual once we are given the ordered basis for a vector space V having a finite dimension. So in the proof, first we shall recall a result that helps us and that actually guarantees us that we can define the linear functionals. We actually first have to prove the existence part, that such kinds of linear functionals exist. So for that thing, we have already done a theorem. So let's recall it here. So recall a theorem from the previous lectures. We had done that if V1, V2, so on, Vn is a basis of V. If this is a basis of V, then and W1, W2, Wn are arbitrary vectors in W. Then there exists a unique linear transformation. Then there exists a unique linear transformation T from V into W such that T of Vi is equal to Wi, where I runs from 1 to n. So we have already proved this theorem in the previous lectures. Now using this theorem, we will directly, it gives us the existence part of this theorem. So in the proof, the linear functionals exist. The linear functionals exist because of the theorem that we have stated above. So because of the theorem which allows us to define linear transformations which map the basis elements, which map the basis vectors of a vector space into arbitrary vectors. Into arbitrary vectors in the image space. So it is this theorem, because this theorem helps us This guarantees us that we can always define a linear transformation, and in fact, such a linear transformation will be unique, that will map these basis vectors into the arbitrary vectors of the image space. So here, the domain space is V and the image space is W, or we can even call it a codomain space. So therefore, we have, by this theorem, we have the existence part of this linear functionals. Now we will show that the set of these linear functionals, which were defined in that spatial way, that fi of pi is equal to 1 and fi of ej is equal to 0 whenever I is not equal to j. Now we'll show that the set is linearly independent set, and it also spans the dual. So now we show the set f1, f2, fn. This forms a basis. So for this what we have to show, we show, so let's call it some b star, beta star. We show beta star is linearly independent and spans v star. Okay, now assume this alpha 1 f1 plus alpha 2 f2 plus so on plus alpha n fn is equal to 0. So first we will show that the set f1, f2, fn is a linearly independent set, and for that thing we will take this linear combination and show that each alpha is equal to 0. So where we have chosen these scalars, where alpha 1 through alpha n, these are the scalars from the field F. So then once we have chosen this to be equal to 0, so then we have, if we evaluate this function under some vector v, so this alpha 1 f1 plus alpha 2 f2 plus so on plus alpha n fn of vi. So if the whole mapping is equal to 0, then this is equal to 0. And in fact, we can see that since this f1, f2, fn, they are the linear transformation. So this scalar, this linear combination is again a linear transformation. Because we have already seen that the sum of any two linear transformations is a linear transformation, and a scalar times a linear transformation is again a linear transformation. So scalar times this a linear transformation, alpha 2 f2 is a linear transformation, alpha n fn is a linear transformation, and again now the sum of linear transformations is a linear transformation, so this is again a linear transformation. So therefore, one we can now, if we evaluate, and since this linear transformation maps is defined to be equal to 0, so it will map every vector into 0. So in particular, it will map this vi into 0. So this gives us alpha 1 f1 of vi plus so on alpha I fi of vi plus so on alpha n fn of vi is equal to 0. But now by definition of these linear functionals, fi of vi is 1 and fi of vj is equal to 0. So this implies alpha I fi of vi, this is equal to 0 because all the remaining terms in this sum are equal to 0. And now this part implies, now since fi of vi is equal to 0, so this part implies alpha I into 1 is equal to 0. And this clearly implies alpha I is equal to 0. So thus, if we replace this I by 1, then 2, then 3 up to n, we will get every alpha I equal to 0. So thus alpha 1 is equal to alpha 2 and so on, and alpha n all are equal to 0. So this means that this f1, f2, fn, this form is a linearly independent set. So finally we check, we show this B star, beta star spans V star. And for this thing, for this, choose F belonging to V star arbitrarily. So choose this arbitrary, and now since this F is a linear functional, so this F is a mapping from, so then F from V into F is a linear functional. So this is a linear function. So that means it maps every vector into some scalar. So thus, F of Vi is equal to alpha I for some alpha I belonging to the scalar field. Now it will map every vector in V into a scalar in F. So in particular, we can set F of Vi is equal to alpha I. So we can write, then we have. We can write it in this way. We can write F of Vi. This is equal to alpha I. This is equal to alpha I Fi of Vi, because Fi of Vi is equal to 1. But now we can again write this is equal to alpha 1 F1 of Vi plus alpha 2 F2 of Vi plus so on plus alpha I Fi of Vi plus so on plus alpha n Fn of Vi. Now here in this sum, F1 of Vi is 0, F2 of Vi is 0, and everything is 0 except this Fi of Vi is equal to 1. And so we again get this alpha I. So now this is actually equal to, this is summation j from 1 to n alpha j Fj of Vi. So that's actually what we have done. So thus we have F is equal to alpha 1 F1 alpha 2 F2 plus so on alpha n Fn. So that is F belongs to the span of B star. So we have completed showing that F is this B star is linearly independent, and now it spans the whole V star because we have chosen this F from V star. So thus the span of beta star is equal to V star. So therefore beta star is a basis of V star. So therefore we have shown that beta star is a base of V star. So now we conclude this in a note. So we note here this beta star. This beta star is called a dual basis with respect to the basis beta of V. So if we have V is a vector space and beta is its basis, then the dual basis obtained in this way is denoted by beta star, and this is called the dual basis of the vector space V with respect to the basis beta of V. So with this thing, we conclude the today's lecture. Now we will take the examples in the next lecture. Thank you so much.